with integrals. Sometimes integrals can get a little complicated, so we want to look for little tricks to make it easier to work through them. One way that we do this is called U substitution, and I don't know why they call it U substitution, why they use the U, but that's what it is. And the idea here is to make a complicated integral a little easier to work with. And one way that you know that U substitution is going to be a good way to go about integrating is if one is the derivative of the other, or at least close to looking like the derivative of the other. So like, let's say here, I have this x squared in this parentheses. Well, if I took the derivative of x squared plus 4, really, it would give me this 2x. So in my mind, I'm like, oh, this looks like this could be a U substitution. So I come in here and I say, all right, usually with U substitution, it's going to be the most complicated thing, and that's in some kind of a grouping symbol. And I'll show you in a minute what I mean by that. But this seems to be the most complicated part. Oops, I forgot to put dx, and that's important. Sorry, this should say 2x squared times x squared plus 4 to the 100th power dx. That's important. All right, so what I would do is I'll say, okay, well, let's let U equal the complicated part. And without looking at the blue here, let's just concentrate on the pink. Du would be 2x, and then the derivative of 4 is 0. So it would just be 2x dx. Now, if I look here, here's U, and here's 2x dx. So I want to go ahead and rewrite it using these. So I'm going to put, this is really the integral, well, this is now the integral of x squared plus 4 is U, so I'm just going to put U to the 100th power. And instead of 2x dx, I have it right here, it's du. So I rewrite it as du. Now take a look at that, what I did. Then I can rewrite the integral. Now, or actually, I can actually work through the integral, and U to the 100th ends up being U to the 101 over 101 plus C. Okay? But this has, your answer needs to be in terms of what it started with, which is the x. So you go back and plug in for U. So what I'm going to have here is, instead of writing U, I'm going to write the x squared plus 4. So that's going to be, instead of U to the 100th, it's going to be x squared plus 4 to the 101. I'm sorry, I said 100, but I meant 101. Plus C. And this is your answer right here. Now that I've given you a kind of a simpler example, just so you know what we're looking at, some good ways to know that it's going to be U substitution. First of all, the most important thing is if it looks like something in there is the derivative of the other part. Some forms that you might see that'll tell you this might be U substitution or time to use it. If I have, take the integral of any of these, if it's something to a high power, you could use U substitution. If it's e to the something, if it's e raised to something power, you would probably be using U substitution. Here's just 1, 2, just so we can separate them. 3, if it's under a radical, if it's something under a radical, you're probably going to, or it might be easier just to use U substitution. If it's something underneath in a denominator. So that if the bottom of a fraction is u substitution, if you have the bottom is a fraction and it's a radical, or if it's under and to a power, we'll just say to the second power just as an example. These are some things that you'll see that might catch your eye and you'll be like, oh, this is going to be substitution. All right, let's go ahead and take some other examples. Let's say this is example 2. I say, give me the integral of 4x over the square root of x squared plus 1 dx. Now this is going to take some time, so stay with me. Make sure you pause if you don't understand something, and then push play and keep writing with us. All right, so this has got a radical at the bottom. So I'll be like, okay, this might be u substitution. And I want to turn this complicated integral into something usable. So I'm going to go ahead and say, let's let u equal x squared plus 1. Then du is going to equal 2x dx. But in this case, I kind of want this to, you just have to, you're trying to force it to look like something that's legit. So I'm just going to think about this for 1 second. And I'm going to say, okay, well, I'm going to rewrite this just so you guys can see this. This is just me thinking. This is a person thinking. So we're not writing this down. We're just thinking. This is a big think bubble. All right, so I'm going to rewrite this as 1 over the square root of x squared plus 1. This is just me trying to show you times 4x dx. Okay? That's the same thing. Let's say that that's like that. I'm just thinking. But the problem is here that I have 2x dx. And there's going to be different ways that you can do this. But I can see in my head, I want this to be 4x dx. I want this to be 4x dx because that's what's up here, 4x dx. So I'm thinking to myself, well, how do I push this to be what I want it to be? And I'm like, well, times 2. So I'm going to multiply both sides by 2. And that'll give me 4x dx. So now I'm going to say, okay, good. Now it looks like what I want it to look like. And there's going to be different ways and different tricks. It's almost like people who do crossword puzzles. You just start getting used to doing them. Once you do a lot of them, they start to look alike. And I'm going to say, all right, well, then 2 du is equal to 4x dx. And then I'm going to substitute. Okay, so instead of writing, and I'll rewrite this again just so that we know what I did, because I'm about to substitute, times 4x dx. All right, so let's go ahead and substitute. So I'm going to go ahead and take, instead of 4x dx here, I'm going to write 2 du. So that's going to be right here. And then I'm going to have 1 over, whoops, I don't like the way I wrote that. 1 over, and instead of the square root of x squared plus 1, I'm going to write u. And now I can go ahead and take the integral. Let's take the 2 out. And that gives me 1 over the square root of u du. And let's go ahead and rewrite that as 2 times u to the 1/2 du. And then I can rewrite that as 2 times the integral of u to the negative 1/2 du, right? Because you're just writing it on the top. And then I'm going to go ahead and write, this is the integral of, no, it's not. Sorry. Now I'm going to go ahead and integrate, and I'm going to have, well, I'm going to add 1, which is really 2 over 2. So that'll give me 2 times u to the 1/2 power all over 1/2, right? Because that's just using the integration. And that's going to end up being 2 divided by 1/2. Keep it, change it, flip it. That ends up being 4 square root of u. But then we have to rewrite that. So let me make some room here. Oops, over 1/2, sorry. Over 1/2. Oh no, that's 4 square root of u. But now I gotta rewrite it. So that's gonna be 4 square root of x squared plus 1. Plus c for your answer. Now what I want to do is just something that you should do. You might want to go back and check this. And checking means, all right, well, let me take the derivative of it and see what I get. So let's say I wanted to check this. I'll check it in green. Remember, this is your final answer, not the check. This is your final answer. Okay, we're done with it. Now we're just going to come over here to the side and check it. Do not check it, get an answer, and put that down as your answer. This is just checking. So I'll say, okay, well, this is really like 4x squared plus 1 to the 1/2. And I'm going to see, all right, well, I would multiply both sides, or not both sides, multiply this exponent over here. And that would be the first part, but this is chain rule. So then I'd have to also take the derivative of the inside. So that'll be 2x. And then you're going to minus 1. So 1/2 times 4 is 2. So I'll do that. Let's clean it up. I have x squared plus 1. 1/2 minus 1 is negative 1/2. And then you got times this 2x still. This is us taking the derivative. And I should write that here just so we have it in our notes. All right, so that's going to equal 4x. And Since this is to the -1/2, that means it's really the square root of x squared plus 1. So your answer does work. All right, let's try. I don't know. Should we get to them? We'll try. Should I do? It's 834. I'll go ahead and do. I don't know if I should get into the trig yet. I'll do just, let's see, let me just try one example and see where we go from there, how long it takes. So if I have something like the integral of sine x over cosine to the third x dx, you're looking here and you have something that could be the derivative of another thing. So cosine could be the derivative of sine, and cosine is in the most complicated spot, the denominator. So let me rewrite this and see what I get. I'm going to rewrite it as I'm going to let u equal the complicated part, u equal cosine x, because you don't want du to be in the denominator. So you want the complicated part in the as u. And then you're going to say, okay, well, then that means du equals negative sine x. But here's the problem. You don't have negative sine x here. You have positive sine x. So I'm going to have to force myself to get a positive sine x here. So that means I really want to divide both sides by -1. So I can have a positive sine x. So I'll divide by -1. And that'll give me negative du is equal to sine x. Okay? So that way I have something to plug in for sine x, negative du. So that means I'm going to rewrite this as what is the integral of, so instead of sine x, I'm going to write negative du. And actually, this is sine x dx, and this should be sine x dx. I always forget the dx. I know everybody does too, so. Okay, let's just rewrite it nicer. So du, negative du is equal to sine x dx. So here's sine x dx. So that's why I'm writing negative du. And then I'm going to write over u, which is cosine to the third. Because also, let me just tell you something real fast. I should have just, for teaching's sake, rewritten this for you guys so that it looked like, let me just do it in a different, so that it looked like this, just so that you get it a little bit more. Some of you might already understand this, but I should have written this as cosine x all to the third power, because you can rewrite it like that, dx. So this cosine x to the third power is the same as cosine to the third power x. All right, so let's go ahead and rewrite this. This is really rewritten as, I'm going to take the negative out, the -1, and I'm going to write 1 over u to the third du, just so that it looks better and we know how to work with it. And then that's equal to negative the integral of u to the negative third power, right? Because I want to take it out of the denominator, du. And then I go ahead and you're going to add 1, and then whatever you get, you're going to put in the denominator. So that's going to be u, -3 plus 1 is -2, all over -2 plus c. -1 times this -2 is going to give me a positive. So I end up with a positive here, and not over -2. Yes, over -2. So I end up with a positive here, and let's just put -1 here so you see what happens. That equals +1/2, see? All over u to the -2 plus c. I'm going to rewrite this as, I'm sorry, there should be no more integral sign because we just did it. All right, so that's going to be 1/2 u to the -2 plus c. And then you got to go ahead and substitute. We got to plug this back in and get it in terms of what you had to begin with, which is going to be 1 over 2 cosine x squared plus c. And maybe I'll go back and explain this step just in case you didn't see. I just rewrote this here. Instead of u to the -2, I just rewrote it again as 1 over u squared, positive squared, that you write it in the denominator as a positive power, and that's why I was able to plug it in like that. And then there's your final answer. You can go ahead and check it on your own. If you have any questions, I'm probably going to do another one next week on just u substitution with trig values. But if you have any questions, you can go to your teacher and always make sure to be great.